So I'm here to talk to you about observability with ZIO-Telemetry. A couple of things. What I will show you here is based on what I've been recently working on at Shell Recharge Solutions, which is part of Shell, and we work on electric vehicles recharging solutions. It's focused on ZIO and ZIO-compatible technologies, such as Dubi, ZIO-gRPC, ZIO-Kafka, STTP, and Zapier. I will use Datadog to show you some screenshots. I have no affiliation with Datadog, just I'm familiar with the tool, and it was easy for me to produce examples using it. So we will go through the notion of observability. I'll show you what are the observability tools we have available out there. You'll see how to use OpenTelemetry on the JVM, how to use OpenTelemetry with ZIO. We will have a look then at ZIO-Telemetry. And I'll show you what I'm working on, which is a library called Theseus to manually instrument your service boundaries using ZIO-Telemetry. What is observability? We use observability because we are interested, first of all, in to know if our service is behaving as expected. We want to be fast in root cause analysis. We want to be able to pinpoint to what is making our services failing. We want to do early detection of errors and react quickly. We want to be fast in discovering what is the nature of an issue. So is it the network? Do we have a timeout? Do we have an internal server error, database issue, whatever? We want also to be able to optimize interaction, especially in a microservices situation. If we see that we are performing twice the same call in a short amount of time, maybe it's time there is some caching opportunity down there. And one thing that we want to have is to be able to produce a service map. So a map that shows us how our services are talking with each other, which transport they use to talk with each other. If your collection tool is advanced enough, it's even able to show you, like, per edge, what is the request rate, failure rate. So you can have a really useful insights about our systems are working. We will use this simple example based on the electric charging world to illustrate what I will talk about. So you have your car, you put your car near a charging column, you plug it in, and then with your mobile app, you start a session. So your mobile app sends an HTTP request to a charging service. This charging service is connected to its own database, and it's connected to a charging hub, which is a system physically connected to the physical column you're attached to. It makes a gRPC call, it receives a response, success or failure. Then the session starts, and after a while, when you're done with your charging, you issue a stop command. And the same thing happens. When the session is started and finished, you post it to Kafka as a message to a billing service that later on will take care of invoicing about this charging session. So what observability tools do we have available to observe such a system? The minimum we can do is logging. So logging is about something that happens at a given time. So it comes with a timestamp and a message. This is how you do it with ZIO. Logging is embedded in ZIO now, so it's very straightforward. And it produces 2 logging events, such as these ones. This is very simple logging. You can make logging more complex, more structured, and you do this through annotations. So for example, here, we added the information about the session and the session step we are in. How do we do this? Also very simple. With ZIO logging, you annotate a region where you run an effect, and all the logging statements within that region will carry this annotation. We have, in this region, we have a smaller section where we are annotating with this session step, which is dynamic, and that will imply the session step to annotate this other effect. So as a result, we see the session ID being available through all the throughout the all the logs, and the session steps being different per iteration. With this, you have your logs are essentially records that you can query, and with this you can already do some filtering and some analysis that gives you some information. But we want to do more than this. One thing also to be aware of is that these annotations in general do not automatically propagate across services. So if I annotate the session ID on the charging service, this doesn't propagate automatically to the charging hub, for example. So this is something that we have to solve. The other tool we have is tracing. So if logs are about something that happens at a given time, traces are about something that happens in a time span. In fact, these colored lines you see here are called spans, and these span all belong to the same trace. So a trace is a collection of span that happen in a given order, and they are connected with each other by the fact that they belong to the same trace and by the fact that there is a child-parent relationship between spans. The length of a span informs us visually about how long a certain action took. And spans also come with attributes. So you can enrich these spans with attributes about the things that happened during that action. Another thing we always want is to correlate traces and logs. So I want to see, when I'm observing some spans, I want to be able to access also to the logs that occurred within that span or within that trace. So tracing and logging are not two alternatives, but they are complementary to each other. Let's talk about OpenTelemetry. So it's an initiative from the Cloud Native Foundation. So Amazon, Google, all the big players are behind this initiative. And it comes as a collection of APIs, SDKs for many languages and tools. And they allow us to collect information in terms of metrics, logs, and traces. In this talk, we will focus mostly on traces. The main things that the OpenTelemetry comes with is an SDK. So in our case, we will use the Java SDK ultimately. It comes with the notion of a context. So every span has its own context. We can think of a context as more or less as a map that carries some amount of information. There is a baggage, and the baggage is some information that is valid for multiple spans. So for example, when you have your user that is authenticated, you want all the interactions and all the spans to carry that user ID. This information goes inside the baggage. OpenTelemetry comes also with a text map propagator, which is a mechanism to inject and extract this context and baggage information to and from a generic carrier. So this carrier can be HTTP, Kafka, gRPC headers, or custom envelopes, you name it. Another things where OpenTelemetry is doing a great effort is to define some semantic conventions, which is define a set of names for standard attributes where we put standard information. For example, when you publish to Kafka, you want to put the topic in a given attribute, and this defines the name of that attribute that should be used when you use OpenTelemetry. So you just import, if you're using Java, a Java library that defines all the static fields that you can then use for your application. Now, when we use OpenTelemetry on the JVM, we have always a collector that exposes our data using a protocol called OTLP, which is sending basically the data that we are collecting, the traces, spans, and etc. In the same way to all the collection applications that you can have down the line. So you send the data in the same way to Datadog or to Grafana Tempo, to Dynatrace, to Jaeger, etc. So it's also a good way not to be locked to only one monitoring solution. The canonical way to instrument your JVM application is use an OpenTelemetry agent. So it comes as a Java agent, so you just have to add one command line parameter. It will come and instrument your runtime code with some code to open spans before something, close spans after something else happened. So this makes the developer experience just great because you don't have much to do if you are a Java developer and you're using this agent. It works with most popular Java libraries out there. But of course, it comes with some negative points, such as there is bytecode instrumentation, which is not what we appreciate the most as functional developers. Also, it lacks, if you look into the code of this agent, it's difficult to see where, which attributes exactly I'm sending when something happens. So this can, this is spread throughout the code in the library. It's also difficult to customize to send some extra attributes. So if I want to, when I send to Kafka, open a span and send something extra than what the agent wants me to send, then it's not straightforward. Also, it instruments all or nothing. So if I adopt the agent, then all the outgoing and incoming channels are instrumented. So I might not be interested in instrumenting health check endpoints, for example, but I have them checked as instrumented as well. Also, the context propagation occurs through thread local things, so it doesn't work with if you use fibers or stuff like that. But if you're using ZIO application, the agent, since a few months, there is also an integration that makes this work with ZIO. So this makes sure that if you open a span, then the context information is transferred correctly so that the agent can keep working as if it does if you're just using a Java application. But in general, this doesn't work with frameworks based on functional effects. So this doesn't instrument automatically, for example, if you're using ZIO-HTTP or HTTP4S routes. They don't get automatically instrumented. On the other hand, if you use HTTP, for example, they get automatically instrumented. So we want to solve this problem. If I'm tracing a microservices architecture such as the one such as this one, you want to see something like this. So when I'm stopping a session, I want to see span for when the incoming HTTP call occurs. Then I want to see a span for the JDBC interaction. And then I want to see the transfer to the gRPC service. And this should be seamlessly show me the multitude of systems as one system, because logically they are one system. And ultimately, I want to see a span for the Kafka interaction. So to have this in place, we will use a library, ZIO-Telemetry, which is fully ZIO-based. You add it as a dependency to your application. It depends on the OpenTelemetry SDK. It uses fiber locals to store the tracing context. And it gives us, for free, the propagation of logging annotations. You remember that logging annotations are not by default propagated. If you use this, they get propagated automatically across services. A simple example of how ZIO-Telemetry works. So here we are opening a root span that in turn runs 3 small effects lasting 1, 2, and 3 seconds. We open a span for each of these sequential effects, and this is what you get in Datadog in this case. So you can see that visually we can see that these things are happening one after the other. This is the same code, just using ZIO aspects. So it's an equivalent code, essentially, just a different style. If I replace that for each with a for each par, I see that the spans are occurring in parallel. So this gives you just visually a lot of information that maybe just looking at the logs you wouldn't catch immediately. Let's see how ZIO OpenTelemetry scores according to this matrix. Before that, let's talk about context propagation. So we have the charging service that calls the charging hub. Let's suppose we're using HTTP for this interaction. What I want to see is having the charging service open a span. Then within the effect in the span, eventually we'll call the charging hub. I want that the charging hub, when it does its own work, opens also a span as a child of the blue span above. So the code, what you have to do is basically take the tracing context at the charging service side and put it inside the carrier. This is the code that you're using for doing that. Then this carrier, in this case, will be HTTP headers, will be sent to the charging hub. On the receiving side, we have the charging hub getting this incoming request carrying the tracing information in headers, and we have to deserialize and reconstruct the context. Once we have that context, we have just to create a child span that would be a child, basically, of the span that we had pending in the charging service. So we have this. This is the code that we use to do this serialization and deserialization of the context. And this same thing happens, in this case, happens for when you're going to HTTP, but it happens in the same way if you are sending things through gRPC or Kafka or JDBC, etc. So the mechanism is exactly the same. So in this library, we are defining an algebra for service boundaries instrumentation, because we want to be precise about what am I sending to the span attributes when I'm doing a given interaction. So for example, when I'm consuming from Kafka, I'm opening a span, and I am declaring here that I will take the record, and from the record, I will put the topic information in these attributes and the partition here. And these are all dictated by those semantic convention fields. So we have one place to look at to see which attributes I am exactly sending. This is easy to customize because you just to enrich this map. And I'm working on what you're doing here is creating a data structure. So if you traverse this data structure to properly, you can build even up-to-date documentation. So you always have aligned documentation about what you're really sending over. Now, this mechanism of serializing and deserializing the context is constant, but the way you want to instrument one technology versus another one can be very different. You can instrument a Kafka producer very differently than how you want to instrument a Tapir route. So what I did is create a base interpreter that does this boilerplate that we just seen for the serialization and deserialization of the context, and to read this generic algebra. And it's generic on the kind of request you're using, the kind of response, the transport, and this interpretation. So how does this work? If you have, for example, you want to send a request through HTTP, you will extend this interpreter by refining the request will be an HTTP request, the response will be an HTTP response, the transport will be the list of headers, HTTP headers, and interpretation will be a decorator of an HTTP backend, of the HTTP backend that you are using. If I'm using for a Kafka producer, then the request will come in terms of a producer record, so a Kafka producer record. There is no response, so I leave this to any, and I'm putting this tracing information in a list of Kafka headers. And I will produce a given Kafka producer tracer that works well with the API of ZIO-Kafka. How does this result? So this is how you produce a record without instrumentation using ZIO-Kafka, and this is how you produce it with instrumentation. So you add this line, and you have all the tracing information carried over. On the consumer side, you usually have a Kafka stream that, for every record, does a given processing. If in that processing I want to make sure that the tracing information is reconstructed, I have just to annotate with this Kafka traced annotation. As a result, this will create, when I'm consuming from Kafka, this span that comes with all the attributes that we declared in our algebra. Same thing, for example, for an HTTP client. So this is how you have a generic, you send a generic request using HTTP, using a HTTP client ZIO backend. What I have to do to trace the outgoing requests is just make a layer around it through this tracing HTTP backend and use that as a backend. And this makes sure that all tracing information gets sent through. So as a result, we will have this HTTP span appearing with all the attributes that, again, compliant with the semantic convention. We do the same for outgoing calls, HTTP, incoming calls, HTTP calls with Tapir, for ZIO gRPC, both on the client and on the server, Dubi, so we open a span every time we make a Dubi transaction, and for ZIO-Kafka. And it's given that base interpreter is easy to instrument other technologies out there. For example, if you're using SQS, you might want to use a custom envelope and put this information in some custom headers and then send it through to SQS. So let's evaluate this. So the developer experience is not as seamless as with the Java agent, but it doesn't make your code much more complicated. It works with libraries, including the ZIO-compatible functional programming libraries that we decided to instrument. Now we have those 5, but it's easy to add more. It doesn't use bytecode instrumentation. We have one place to see how the attributes are built. We can customize to send extra attributes. We just have to extend that algebra. And we send tracing information only for things that we are actively instrumenting in our code. So we don't have this all or nothing. And the propagation occurs through fibers, through ZIO fibers. So in conclusion, with a language such as Scala, we can live without bytecode instrumentation, and tracing doesn't make an exception for this. Because all you need are higher order functions and some syntax capabilities to enrich your classes. The developer experience remains acceptable with this approach, and you keep your code in control because you're able to see, looking at one place, where things are happening. And we defined a solid and extensible foundation to derive different interpretation and to be able to instrument manually different technologies. The code is available here. It's very work in progress, so the API is not final, but if you're interested, please have a look. And I'm curious to hear any feedback, suggestions, etc. That was it.